At our last topic for this unit, where we look at a new method for integrating functions, aka finding antiderivatives of functions, known as U substitution, the topic of 4.6. So we may ask, why do we need a new technique for integration? Well, the reason is that the integrals we've seen so far mainly involve functions that have known antiderivatives, meaning more or less as long as we know the antiderivative, we don't have to do too much work in evaluating the integral. But now we're going to take a look at cases that contain a composition of functions, aka f of g of x, like the chain rule in reverse, okay? And integrals, where one part of the integral is integrand, is a derivative of another part of the integrand. So like the integral of f of x times f prime of x d of x. In this case right here, we can't just rely on known antiderivatives, so we have to come up with a method in order to deal with these types of integrals. And this is what we call U substitution. U substitution is essentially the chain rule in reverse, so finding the antiderivatives of functions that require a chain rule, okay? And even though it seems quite abstract and esoteric right now, looking at these very abstract integrals and notations right here, in practice it's not too bad, so the more we get the hang of it, and the more we practice with it, the more you'll see it's not too bad. Okay, so the method of U substitution, so let's say I have these two integrals right here, okay? Integral of f of g of x times the derivative of g of x, and the integral of f of x times the derivative of f, okay? So, in the first case, we're going to set g of x, our inner function, equal to u, just as we do with the chain rule, okay? In the second case, we're going to set f, okay, equal to u. The remaining part of the integral is what we're going to call the leftovers. In the first case, our leftovers are going to be g prime of x, d of x, okay? So whatever does not contain a u is going to be leftovers. So f of u is not going to be a leftover. G prime of d of x, g prime of x dx will be our leftover. And in the second case, okay, we set f of x equal to u, which means our leftover is going to be f prime of x dx, okay? What we're going to do is, with the u's that we've chosen, we're going to take the derivative of u with respect to x. In this case, in the first case, this means that our derivative of u with respect to x is going to be equal to the derivative of g, since we chose u to be equal to g, okay? And in the second case, it says section case right here, there's a typo right there. In the second case, okay, our derivative of u with respect to x is going to be equal to the derivative of f, since we chose f to be equal to u in our second case, okay? So what we're going to do is we're going to treat du over dx as like a fraction, okay? So what we're going to do is we're going to solve the equation for du over dx in each case for the leftovers, okay? In the first case, this means rewriting, we're not going to solve for leftovers, we're going to solve for, we are going to solve for leftovers, excuse me. I'm all over the place, okay? So in the first case, this means we're going to rewrite du over dx equals g prime of x to get du equals g prime of x dx. Okay, so we're solving for our leftovers. We want to get g prime of x dx on the right-hand side, since this is our leftover in the first case. In the second case, we're going to rewrite du over dx equals f prime of x to get du equals f prime of x dx, since our leftover in the second case is f prime of x dx. Okay? So now what we can do is we can substitute u and du into our integrals, okay? So as a result, we're going to get the integral of f of g of x times g prime of x d of x is going to be equal to the integral of f of u du, okay? So g gets replaced with u, and then g prime of x dx gets replaced with du, okay? Again, this is the big step right here in step 2 and step 3. We take the derivative of u with respect to x, and then we solve for our leftovers with this equation that we get, okay? And then in our second case, f of x, f prime of x, d of x is going to become f of u, okay, du. So as a result, we're going to evaluate the integral to get f of u, okay? So let's say little f has a known antiderivative, big F. So as a result of replacing, we can replace our inner function and our derivatives with u, and that's going to allow us to evaluate the integral to get the antiderivative of f with respect to u. And then we can substitute the appropriate expression for u back in to get our antiderivative. So in the first case, the antiderivative with respect to u is going to become the antiderivative of g of x. We replace u of g of x. And then the antiderivative of u of f with respect to u in the second case is going to become f of x. And it says g of x right here, but that's a typo, okay? So this seems like a lot of steps, but in practice, it can be carried out quite quickly, all right? So that's what we're going to do here is look at some sample problems and get some more practice in class until a point that we can do this like the back of our hand, okay? As with most things in math, practice is more essential than the actual process. The process itself can seem much more abstract and esoteric and advanced than it really is. So let's look at an example right here. We have substitutions. We're going to use U substitution with compositions, specifically an integrand that contains a composition. So let's take a look at the integral of e to the 4x dx. So here we don't just have e to the x, we have e to the 4x. So we have a composition of functions here. We can't just write down our antiderivative as e to the 4x. We have to use U substitution here. So we identify we have to use U substitution, and we identify that as an inner function of 4x. All right, so we're going to have e to the u, and our leftover that does not contain a u is just going to be just dx. Okay? So we set u equal to 4x. In our second step, we now take the derivative of u with respect to x, which is going to give us du over dx equals 4. Okay? So now what we're going to do is we're going to solve this equation for our leftovers, okay? In this case, our leftover is dx, so we're going to solve this equation for dx, which means we're going to multiply both sides by dx to get du equals 4 dx, and then we're going to divide both sides by 4 to get du over 4 equals dx, okay? So now we're going to rewrite our integral. We have e to the 4x dx equals e to the u du over 4. Okay? And that's going to equal 1/4 e to the u du. Okay? So we can factor out the 1/4 right here. So we've substituted u equals 4x and du over 4 for dx into our integrand now. So now we can evaluate this integrand because we do know the antiderivative of e to the u. The antiderivative of e to u is going to be just e to the u plus c. So as a result, we get that 1/4 e to u plus c is going to be our general antiderivative. And so now we can replace 4x with u with 4x to get our general antiderivative. So this is U substitution in practice. Now we're going to take a look at a second case where we have substitution with derivatives, okay? AKA where we have an integral where one part of our integrand is the derivative of another part of the integrand. So evaluate 6 sine of x times cosine of x dx. So in this case right here, we don't have any inner functions, but we don't know the antiderivative of sine of x, cosine of x off the top of our head. So what we can take note of is if we look at this integrand right here, we can take note of the fact that cosine of x is the derivative of sine of x, okay? So we're going to choose u to equal sine of x, okay? So as a result, choosing u equal to be equal sine of x, the leftover is going to be 6 cosine d of x, or dx, excuse me. So in our second step, we identify u equals sine of x. So we're going to take the derivative of u with respect to x, which gives us du over dx equals cosine of x. Okay? So as a result, we're going to get du equals cosine of x dx. Okay? We haven't completely solved for our entire leftovers yet, though. We have du equals cosine of x dx, which means now we need to multiply both sides by 6 to get 6 cosine of x dx. So we're going to get 6 du equals 6 cosine of x dx, and that allows us to solve for our leftovers. So now we can rewrite our integral as u times 6 du. We replace 6 cosine of x dx with 6 du, and we replace sine of x with u. Okay? So that's going to give us 6u du for our integrand, okay? And we can evaluate this integrand right here using the power rule in reverse. Specifically, we know the integral of 6u du is going to be equal to 3u squared plus c. So now we can replace u of sine of x, which gives us 3 sine squared of x plus c as our general antiderivative. So now let's look at what happens if we consider substitution in definite integrals. If we're working with a definite integral with a lower bound of a and upper bound of b and substitution is required, say we have the integral from a to b of f of g of x times g prime of x d of x. Oh man, that's a mouthful right there. All right. The substitution of u for g of x means that the resulting lower bounds must be in terms of u. So what we do is we plug in a for x and b for x, and that gives us new lower and upper bounds. Specifically, the new lower bound is going to be g of a instead of a, and new upper bound is going to be g of b instead of b. So in this case, we can rewrite our integral as u of 2 as the definite integral from u1 to u2 of f of u du. And then assuming again that f has a known antiderivative, you can evaluate the above definite integral strictly in terms of u by using the first fundamental theorem of calculus. So by first fundamental theorem of calculus, the definite integral from u1 to u2 of f of u du will be equal to the antiderivative evaluated at u2 minus the antiderivative evaluated at u1. Again, this seems quite exoteric in practice, in theory, but in practice, it's something that can become quite secondhand nature with enough practice and exposure. So let's take a look at an example here real quick. Let's say we're looking at the integral from 0 to square root of pi of x sine x squared, okay, dx. So we don't know the antiderivative of x sine x squared at the top of our head, so we have to use U substitution, okay? So we identify here that we have an inner function of x squared, so we're going to set u equal to x squared, and then thus our leftovers are going to be x times dx. So as a result, we're going to take the derivative of u with respect to x, and that's going to give us 2x, all right? So now we're going to solve this resulting equation for x dx. So du is going to equal 2x dx, and we divide both sides by 2, and we get that x dx equals du over 2. Next, we need to set up where our new lower bounds and upper bounds are, okay? So for u equals x squared, we're going to have our new lower bound is going to be u of 0 equals 0 squared equals 0. And we're going to have u of square root of pi equals square root of pi squared, which gives us just pi. So as a result, our integral is going to become 0 to pi. We replace our lower and upper bounds with 0 and pi, okay? Times sine of u, du over 2. We replace x squared with u and replace x times dx with du over 2. So that gives us 1/2 the integral from 0 to pi of sine of u du. So as a result, okay, we can evaluate the integral of sine of u du. We know that's going to give us an antiderivative of negative cosine of u, and then of course multiply by that 1/2. And then we can evaluate this integral by using first fundamental theorem of calculus. So we're going to have negative 1/2 cosine of pi minus negative 1/2 cosine of 0, which is going to give us 1/2 plus 1/2, or just 1. And thus we have an example of how we can use substitution to evaluate a definite integral.